Hello, and welcome to our lesson about limits at infinity and horizontal asymptotes. Let's get started. First, we're going to investigate the function 3x squared divided by the quantity x squared plus 1. For this rational function, we're interested in answering the question, what happens to the y values of the function as x increases without bound? Let's investigate this question using our graphing calculator. I've already graphed the function f of x equals 3x squared over the quantity x squared plus 1. You can see from the graph that as x gets large, the y values seem to increase, but they seem to do so with an upper bound. It seems to be about 3, judging from the graph. Let's look at a table of values, see if we can verify this. We press Control T on our calculator to pull up the split screen, but I want to be able to select the x values, so I'm going to hit Menu, and then Table, and then Edit Table Settings, and change the independent variable from Auto to Ask. This allows me to enter in the x values that I want to examine. We want the x values to increase without bound, so I'm going to pick a sequence of x values here that increase very quickly. If I start out with 10, you can see that the y value is about 2.97. If I then jump to 100, increase by a factor of 10, the y value is 2.997. These values seem to indicate that our guess, by looking at the graph, was correct. The y values seem to be getting closer and closer to 3 as x increases. Well, let's look at an even larger x value, 1,000. Oh, well, we see something interesting now. The calculator just says 3, but remember, that's not exactly 3. That is just very, very close to 3. The unrounded value is displayed down here at the bottom when I highlight that cell. It's 2.999997. Well, if we're not convinced, we can go even further, maybe 10,000. And we see something similar here. Again, a value that is very close to 3, even closer than the one before. So as x increases without bound, it seems like the y values are getting closer and closer to 3. Now, what about the other direction? As x goes off to the left, that would be x decreasing without bound, or x approaching negative infinity. Now, by symmetry, it seems that we should have the same limit. Let's see if we can verify that using the table. I'm going to have to switch it back over to Ask again. Now I can enter in negative values. Negative 10, negative 100, negative 1,000. And you can see that these values are also getting closer and closer to positive 3. So in your notes, I've summarized this in a table of values. When the x values increase without bound, 0, 1, 10, 100, all the way and continuing up to positive infinity, the y values seem to be getting closer and closer to 3. We can show this in several different ways. I can say that f of x approaches 3 as x approaches infinity, or I can write that the limit as x approaches infinity of f of x is equal to 3. When x decreases without bound, x equals negative 1, x equals negative 10, negative 100, all the way decreasing more and more without bound, you can see the y values again get closer and closer to 3. So f of x approaches 3 as x approaches negative infinity, and the limit as x approaches negative infinity of f of x equals 3. So the concept of a limit as x approaches infinity means the following. What happens to y as x increases without bound? We are interested in what is happening to the y values as the curve gets farther and farther to the right. We also want to talk about limits as x approaches negative infinity. This would mean what happens to y as x decreases without bound. This means what is happening to the y values as the curve gets farther and farther to the left. The terminology we use is the following. The limit as x approaches infinity of f of x when x increases without bound, and the limit as x approaches negative infinity of f of x when x decreases without bound. Notice that it doesn't make any sense to talk about right and left-hand limits at infinity. There's only one way to approach infinity. Let's look at some graphical examples. These are problems that you could probably have solved in pre-calculus. We're just putting them in terms of limits. So for this first graph, it looks like a nice parabola. As x approaches negative infinity, we're traveling along the graph following its left-hand end behavior and noticing that the y values are increasing without bound as well. So the limit as x approaches negative infinity is positive infinity. The same is true of the right-hand end behavior. As we move to the right, I need an ink pen to do that. As we move to the right-hand end behavior seems to be increasing to positive infinity as well. In example 2, it looks kind of like a cubic curve. The left-hand end behavior seems to be increasing without bound as x decreases without bound. So since we're going up and to the left, the limit as x goes to negative infinity would again be positive infinity. But over on the right-hand side, as x increases without bound, it looks like the y values are decreasing without bound. So we would say that this limit is negative infinity. This corresponds to our idea of end behavior from pre-calculus. A couple more examples. These functions have horizontal asymptotes. In example 3, it looks like y equals 4 is a horizontal asymptote for the left-hand end behavior. So the limit as x approaches negative infinity of f of x is 4. The right-hand end behavior seems to obey the asymptote y equals negative 2. So the limit as x approaches positive infinity of f of x is equal to negative 2. Now, example 4 is a bit more interesting. Notice that the graph seems to oscillate around a horizontal asymptote. This is fine. This still obeys the definition of a limit. As x decreases without bound, in other words, goes to the left, the f of x values, the y values, get closer and closer to, in this case, 1. On the right-hand side, as x increases without bound, although we have this oscillation, the y values are getting closer and closer and closer to 0. Now, in this last example, I want you to pause the video and think about this one for a second and then come back. I'll give you a moment. Okay, so we'll do the right-hand end behavior first. These values, while they are oscillating, and the values seem to be oscillating less and less, they seem to be getting closer and closer to the slant asymptote. Well, while we're getting closer and closer to that slant asymptote, notice that the asymptote itself is continuing to increase. So there is no fixed y value that we're getting closer and closer. That y value just gets bigger and bigger and bigger. So the right-hand end behavior would be positive infinity. On the left-hand side, notice that this curve just continues to oscillate like a cosine curve, up and down, up and down, up and down, between positive and negative 4. There is no single y value that the function gets closer and closer to as x decreases without bound, goes to the left. So we have to say that this limit does not exist. If you'd like to see more graphical examples of its nature, follow the QR code embedded here to get some additional assistance. Let's take a look at an algebraic example. This is the limit as x approaches infinity of the function 5 minus 2 divided by x squared. We can use some of the logic that we studied in the last section to help us reason through this. In this case, let's focus on the fraction 2 over x squared first. The denominator of this fraction is x squared, and x is going to infinity. If I take a large number, x approaching infinity, and square it, it's going to be even bigger. So this denominator, x squared, can be thought of as approaching infinity. But the numerator is always going to be 2. So we have a fraction where the numerator is approaching 2 and the denominator is getting bigger and bigger and bigger. Well, that should make sense that that fraction, 2 over x squared, must be getting smaller and smaller and smaller. So we have a limit that's equal to 5 minus 0. The constant term is always 5. That does not change. The fraction 2 over x squared gets smaller and smaller and smaller, approaches 0 as the denominator gets bigger and bigger and bigger while the numerator stays the same. So our answer is 5. What we've used here is a type of logic where we're analyzing the ratios of quantities. Often we can analyze limits involving 0, infinity, and constants by simply understanding some basic things about these ratios. So this first example here, constant over infinity, we're talking about a limit. This is not arithmetic, so this is not constant divided by infinity in the arithmetic sense. This is a fraction whose numerator is approaching a constant and whose denominator is approaching infinity. And as we've just seen, that ratio is always going to approach 0. This is also going to be true if the numerator is approaching 0. It's simply going to, the quotient is simply going to approach 0 very quickly. Okay, let's take a look at some other cases. What if the numerator were approaching infinity and the denominator was approaching a constant? Well, the numerator is getting bigger and bigger and bigger, the denominator is staying the same, so eventually, even though we're dividing by a constant, that ratio must also become infinite. It just gets bigger and bigger and bigger. But what about infinity divided by 0? The numerator's getting bigger and bigger, denominator's getting smaller and smaller. Well, just like in the constant case, it just happens a lot faster. If we're dividing by smaller and smaller numbers, that means the quotient must be getting bigger and bigger and bigger as well. Okay, let's take a look at these. These don't have infinity in them. They look a bit more like the ones we looked at in the previous section. If the numerator is approaching 0 and the denominator is approaching a constant, it doesn't matter how big or how small that constant is, the ratio must be approaching 0. If we flip it upside down and it's the numerator that's approaching a constant and the denominator that's approaching 0, the denominator is getting smaller and smaller and smaller, so we're dividing a constant by smaller and smaller numbers, so the ratio must be approaching infinity. This is the very common situation that we saw in the previous section when we were studying infinite limits. Now, these last two, we've already studied 0 over 0 quite a lot. We saw many limits in section 2.5 of this form, and we called that an indeterminate form. In fact, infinity divided by infinity is also indeterminate. So we're going to draw a line here, and we're going to label these as indeterminate forms. They're called indeterminate because their value cannot be determined from this form. We must do algebraic simplification, rewrite them in another form so that we can do more effective analysis. The goal is to take one of these indeterminate forms and algebraically transform it into one of the forms at the top so that we can evaluate its value. Okay, let's take a look at some more examples. Well, the cover-up method is a method that I think I like a lot that can be used to evaluate many limits at infinity, because these quantities that are becoming infinite often override quantities that grow less quickly. For instance, if x is going to infinity, the numerator of this fraction, 2x minus 1, well, the minus 1 doesn't actually matter very much when x gets very, very large. A very, very large number multiplied by 2 is going to be so much bigger than minus 1 that the minus 1 doesn't matter. Same thing's true in the denominator. The x grows faster and faster and faster as x goes to infinity, but the 1 will always be 1. So we can cover up the minus 1 in the numerator and the plus 1 in the denominator and effectively rewrite this in an equivalent form. We can just say it's the limit as x goes to infinity of 2x over x. Well, that seems pretty straightforward now. The x's cancel, and now we just have 2. Well, the limit of a constant is going to be that constant no matter what x is doing. So our limit here is 2. Pretty simple. Let's use the cover-up method to analyze these three rational functions. Notice here that the limit is x is going to infinity. The cover-up method only works for limits at infinity. We have to be very careful not to use this method in other cases. So in this case, we're going to look at the fastest growing term in the numerator, which is the 2x, and the fastest growing term in the denominator, the 3x squared, and we're going to look at their ratio. So this limit is equal to the limit as x goes to infinity of 2x over 3x squared. In this case, the x's cancel, but not completely. We're going to be left with a factor of x in the denominator. So this is equal to the limit as x approaches infinity of 2 over 3x. Well, now, based on the logic of ratios from the previous slide, we know that the numerator is always 2 and the denominator is approaching infinity because it's 3 times numbers that are getting bigger and bigger and bigger. So 3x has to approach infinity. A constant over infinity must go to 0. So this limit is 0. In part B, we got a similar looking function, but I want you to notice that we've changed 2x squared in the numerator. So now the fastest growing term in the numerator is this highest degree term, 2x squared. So this is equal to the limit as x approaches infinity of 2x squared over 3x squared. In this case, the x squareds do cancel completely. So our limit is just the constant 2/3. And then finally, let's use green ink this time. In part C, it's the limit as x goes to infinity of 3x cubed plus 5x over 3x squared plus 1. So we can drop off the plus 5 and the plus 1 as we've done before. We have the limit as x approaches infinity of 2x cubed over 3x squared. The x cubed divided by x squared is just x, so this is the limit as x approaches infinity of 2/3 x. Well, x is going to infinity, so multiplying a very, very large number times 2/3 is still going to be a very, very large number, so our answer is positive infinity. There's an interesting question here. Would it have made any difference if x had approached negative infinity in these problems? Well, as in these cases, it wouldn't. In part A, if this had been negative infinity, 2 over 3x, the denominator would have been negative, but because the denominator is still growing without bound and the numerator is constant, the fraction still goes to 0. In part B, if x were approaching infinity, the x squareds would still cancel out, so it's not going to matter at all that x is approaching infinity. The answer would still be 2/3. And then finally, in part C, what would be the difference? Well, in part C, as x approached negative infinity, if we do C again, the limit as x approaches negative infinity, the algebra is still going to be the same. It's still going to reduce down to 2/3 x, but this time x is going to negative infinity times a positive 2/3, so our answer is negative infinity. What we've seen here is that all three of these are rational functions. When the limit as x goes to positive infinity is a constant, like 0 or 2/3, that's going to be the same no matter whether x is approaching positive infinity or negative infinity. However, if the limit is infinite, the end behaviors may be different. One side might be positive infinity, and one side might be negative infinity. There's actually a general rule of thumb for rational functions that you may have memorized in pre-calculus. Notice that our cover-up method results in a limit of 0 when the degree of the denominator is greater. It results in a limit of a constant, that's the ratio of the leading coefficients, if the degree of the numerator and the degree of the denominator is the same. And our cover-up method results in a limit of either positive infinity or negative infinity if the degree of the numerator is greater. Let's summarize on the next slide. If the degree of the numerator is less than the degree of the denominator, then the limit of the rational function is 0. If the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function is the ratio of leading coefficients. If the degree of the numerator is greater than the degree of the denominator, then the limit of the rational function is always going to be either positive or negative infinity. And you're going to have to do a little bit of thinking to figure out whether it is actually positive or negative. So in class, we're going to pick up with a couple of more complicated examples, but this is where I'm going to leave it off for now. I'll see y'all in class next time.